Okay, guys, so we don't have that many slides today, but we do have a lot of information to cover. So we're going to go through 4.7, 4.8, 4.9, which is all going to kind of be focusing on things that affect weather around the world. So we're going to start with the basic solar radiation and Earth seasons. An important vocab word we're going to need to know for this section is insolation. So that's the amount of solar radiation or energy from the sun's rays that are reaching a specific area. So it can actually be calculated mathematically. So if you look here, it's measured in watts per square meter. So if we wanted to actually calculate it up, we could calculate this whole area here in square meters, and then how many watts of sunlight are reaching that area and divide. So the watts divided by the square meter would give us our insolation rate. So, lots of essential knowledge in this section here. I'm not going to go through all of those right now because I'm going to do that in the notes, but just understand our main learning objective for today is to explain how the sun's energy affects the Earth's surface. And your practice FRQ is going to be just to describe characteristics of an environmental concept, process, or model represented visually. So let's go ahead and start with some things that are going to determine solar intensity. And the first one we're going to talk about is latitude. So, a couple of things that are going to determine how intense the sunlight is in an area are going to be the angle, so how directly the rays are striking Earth's surface, and the amount of atmosphere that the sun's rays have to get through, and so they can reach the surface. So let's remember what latitude is. So that's just how we measure from the equator. So the equator would be 0 degrees, and then the North and South Pole would each be 90 degrees. So 90 degrees north, 90 degrees south. And when we think about areas on Earth, it's obvious when you think about the equator that you can kind of generalize that the equator is going to be getting more solar radiation, because when we look at the type of plants and things that grow there, we see a lot more variety of plant life, animal life around the equator. But let's talk about why that is. So it's actually because of the angle that the rays are hitting Earth's surface. So because of the curvature of the Earth, so how it's curved, it's round. The equator is essentially perpendicular to the sun, so the Earth's rays are going to be much more concentrated here. They're hitting at a more direct angle, as opposed to a more oblique angle that we'll see up here. So they're hitting at a more direct angle, which means they're more concentrated on a smaller area. So we'd have more watts coming in, we'd have a smaller area, so we would have higher insolation there at the equator. Whenever it starts to strike either at the very northern latitudes or at the very southern latitudes, we have more of an oblique angle because of how pronounced that curve is there. So with that oblique angle, we're going to actually see the sun spreading out the area that its rays are hitting. So we have less rays actually making it to Earth's surface because there's more atmosphere to pass through. So more rays are getting absorbed. And then that area is larger. So less watts, more area is going to lead to a lower insolation. So you can kind of see that demonstrated here. If we were to try to make like a nice little angle here at the equator, we've got a pretty direct angle, but for our higher latitudes, we've got a much larger angle, so the sunlight's going to be spread out. So overall, we can understand that the equator does have higher insolation than higher latitudes because of that direct angle, and there is less atmosphere there that the rays have to work their way through. So this is another really good diagram to just show you that exact same thing we just talked about. So you can see our atmosphere is much shorter here at the equator, and our rays are hitting directly. So there's a smaller surface area that we're hitting. So our solar insolation on average around the equator is going to be about 400 watts per square meter. But as we move higher up, We can see that atmosphere is a little thicker, so not as many rays are able to make it to the surface. There's a wider angle, so that gives us a larger surface area for those rays to be spread out across. And so here at our North Pole, we're going to average only about 200 watts per square meter. So let's talk about how those couple of different things there are going to impact seasons here on Earth. So we hopefully know that the Earth is tilted on its axis about 23.5 degrees. And because of that tilt, that's going to change the angle that the sun's rays are hitting the Earth based on what time of year it is. So this is going to cause a variation in insolation, and this is also going to create a variation in length of day and seasons. So understand that the tilt of Earth's axis stays fixed during its orbit, so it's always tilted at 23.5 degrees. So depending on where the sun is in its not the sun the Earth is in its orbit of the sun, we're going to have different places getting different levels of insolation. So let's start with our June and December solstices. So here you can see this is our June solstice over here. And because of that tilt of the equator, of the Earth's axis, we actually can see that above the equator, our northern hemisphere is tilted more towards the sun. So that's going to increase the amount of sunlight hitting the northern hemisphere. So here we would be going into our summer, and because the southern hemisphere is tilted away, they would be going into their winter. If we travel directly across, we can see the opposite happens here. So now we are tilted further away in the northern hemisphere, so we would be moving into winter, and our southern hemisphere is closer, so they would be having their summer. Another important thing to notice here is that during these times, the sun isn't directly concentrated on the equator. If you look at your March equinox here, you can see the sun is very direct onto the equator, whereas if we look at our solstices, the sunlight is actually going to be concentrated on the June solstice about 23.5 degrees north of the equator, which we call the Tropic of Cancer. And in our December solstice, it's going to be concentrated 23.5 degrees south of the equator, which is our Tropic of Capricorn. Then you can see on our equinoxes, so this is our March equinox, this is our September equinox, our north and our south poles are equally facing the sun. So this is where we're going to be moving, from winter to summer, or summer to winter. And so the way I like to think of this, equinox reminds me of the word equal. So each hemisphere is getting equal insolation at that time. So as we move forward, this is the same diagram we were just looking at, just with a little bit more detail in it. So understanding that the tilt of that axis is going to change the angle of insolation. It's going to change the length of day. It's also going to change what season we're in. So I want you to do me a favor, and I don't want you to try to completely memorize this diagram and every single thing in here, because that's just a lot. But I want you to think logically about how the angle of Earth's tilt is going to change the amount of direct sunlight or the angle of insolation. So let's just talk about a couple of them. So let's look at the March equinox. So you can see there our equator is directly facing the sun. We're getting the most direct insolation right there at our equator. So that means we're going to have equal sunlight in each equator, which is going to make it spring if we're in the north, or fall if we're in the south. However, when we look over here, we can see that now our northern hemisphere, because of that 23.5 degree tilt, now our northern hemisphere is tilted more towards the sun than the southern hemisphere. So this is going to give us longer days in the northern hemisphere. So that's going to be like our summer days where we're getting sometimes more than 12 hours of sunlight, and it's going to equal very short days in the southern hemisphere because they are in their winter. So just remember, whatever we are in our northern hemisphere, it's opposite for the southern hemisphere because of that tilt. All right, going back to this idea about albedo, I want you to remember albedo is the proportion of light that is actually reflected by a surface. So remember, the more light that is absorbed by a surface, the more heat a surface is going to be able to produce through that infrared radiation. So understand that albedo doesn't necessarily impact insolation itself, but it does determine how much of that insulated light is absorbed, and then that determines temperature. So we know that surfaces that have a higher albedo are going to reflect more light. Um, and so that means they're going to absorb less. So things like ice and snow, they're absorbing less. So they're going to have those cooler temperatures. Think about something like a mirror. A mirror has 100% albedo, everything is reflected off of that. You can also think about the difference between a white shirt and a black shirt in the summer. If you wear a white shirt, that's going to absorb less of the sun, so it's going to make you feel cooler. If you're wearing a black shirt, more of the sun's rays are going to be absorbed, so you're going to feel warmer. So surfaces with low albedo reflect less light and absorb more of those solar rays. So an example there would just be plain water without ice and snow. So they're going to absorb more heat. So what we see here because of this albedo is surface temperature being affected. So when sunlight gets absorbed by a surface, like I just said, it's going to give off that infrared radiation, which we can actually feel as heat. So areas that have a lower albedo absorb more sunlight, so they're warmer. And we can see that in what we call an urban heat island or the urban heat island effect. So when we look at urban areas, they tend to have a lot of blacktop, asphalt buildings, which are going to have low albedos. So they're going to absorb a lot of those rays from the sun, and they're going to release that infrared radiation as heat. So what we can see is that even if we compared an urban area to a rural area in at the same latitude, technically we should expect to see them to have similar temperatures. But because of the difference in albedo, that's not going to be the case. We're actually going to see the urban areas being much warmer than the surrounding rural areas because the rural areas are not going to be absorbing as many of those sun rays, so they're not going to be releasing as much infrared radiation and heat. So our polar regions are colder because of the higher albedo. Not necessarily, yes, the insulation does play a role in it, but the temperature is going to be more affected by our albedo. So for our practice FRQ here, I want you to identify which season is taking place in the northern hemisphere in our little diagram that we have. And I want you to describe how the tilt of the Earth's axis is responsible for Earth's seasons. So a really good example here would be to just simply state, because it says to identify what season is taking place. So in the northern hemisphere, we would be experiencing spring, summer, winter, fall, whatever you think, okay? Um, and then describe why that is because of the tilt of the Earth's axis. All right, so that's going to move us right into 4.8, where we're going to look at Earth's geography and climate. So here we're going to be looking at regional factors like mountain ranges, wind patterns, body of water that are going to affect the local climate of a region. So our learning objective here is to describe how Earth's geography affects weather and climate. And our FRQ is going to be to explain relationships between different characteristics of environmental concepts, processes, or models represented visually. And this FRQ is a little tough, so I'm going to help you with it a little bit. So let's just remember that climate in general is largely determined by insolation. So that latitude is going to either increase or decrease the angle of insolation and how much atmosphere the sun has to pass through. So hopefully we can remember that higher latitudes get less insolation, so they're cooler, which means they get less precipitation, and that the equator is going to get the most intense insolation, which is going to lead to higher temperatures, which causes the air to rise. So as the air rises, it cools down, it condenses, and that water vapor that's in the air is going to fall as precipitation. Now, as that air falls, or as the water falls as precipitation, that air is going to start to cool down, it's going to dry out, and that's going to lead to that lower precipitation around that 30-degree mark because of those Hadley cells. So just don't forget, because this section here really takes a lot of things we've talked about in the last unit or so and kind of starts to put them together. So just remember that more insolation at our equator, less insolation at our higher latitudes. But some other things that are going to play a role in climate and local weather is geography. So mountains, we're going to talk about those a lot. They're going to disrupt wind. They're going to produce what we call a rain shadow. You tell those poor children that you are sorry for interrupting their learning. Tell them. Tell them. Yeah, it's all your fault. Get out of here. All right, so like I said, those mountains are going to disrupt wind patterns. They're going to produce rain shadow effects. And then our oceans are also going to play a really important role. They're going to help moderate temperature, and that's because the water is actually going to absorb heat when the land is very... Okay, I'm sorry, guys. The mail came. So they're going to absorb heat when the land is very hot, and they're actually going to release heat when the land is cooler. So they help to moderate and stabilize temperatures. And then they also add moisture to the air. So let's talk about those rain shadow effects in a little bit more detail. Now, these are going to be most prominent whenever we have mountains that are near coasts, but they do occur regardless of whether they're near coasts or not. It's just the effect is larger when they're near a coast. So what we see with the rain shadow effect is that you're going to have that warm air blowing in from the ocean, and because it's warm, it's going to have a lot of water vapor in it because it's going over the ocean. So that warm air rises up to the top of mountains. As that air starts to cool, the water vapor condenses, falls as rain. Then what we see is that we see our wind moving over our mountain, and it is going to be very dried out now. There's not going to be all that moisture in it. So what we tend to see is on one side of a mountain range, a lot of precipitation, a lot of lush vegetation, and then on the far side, we see much more desert type areas. So we would call this the windward side of the rain shadow effect. So our winds blowing from 0 to 30 degrees are blowing east to west. So that would make this right here the windward side. So whatever side the wind is blowing to is the windward side. So if we are from 0 to 30 degrees, the windward side is going to be on the east. And then the dry air goes down the other side, and we call that the leeward side. So let's look at a real example of this. So we've got our equator here, which is 0. We've got 30 degrees west right there. So remember that we've got our eastern trade winds happening. So blowing that warm, moist air from the Atlantic across South America. So here in South America, we can see the Andes Mountains. Now, one thing I want you to understand, because a lot of times with this rain shadow effect, you would look at this diagram and you would see, well, the mountains are right here. They're really close over here to the South Pacific Ocean. And so we're going to see our lush vegetation on the coast and our drier areas inland. But you have to remember the direction the winds are blowing. So because the winds are blowing east to west, they're actually going to be bringing all that air across South America. So the windward side is on the east because of the trade wind. So the eastern side of the Andes would receive very heavy rainfall. So all of this inland area is going to where we see that lush tropical rainforest. And then the leeward side over here on the coast is going to be where we're going to have that warmer air with less water, giving us the Atacama. Wow, guys, I can't talk today. Atacama Desert, which we see right here. You can see it's also about that 30-degree mark. So with that Hadley cell bringing that dry air down, it's really got a lot going on there to make it dry. Okay. So that's what that's saying right there. So high pressure, dry descending air from the Hadley cell. So between the Hadley cell and the rain shadow effect, very, very dry in that area. So when we look at these two diagrams, like I said, this is really starting to put a lot of those pieces together. So if we look over here at our global wind patterns and our solar radiation, so these numbers over here are going to be our precipitation levels from high to low. We've got our latitude over here. So we know from 0 to 30. We've got those winds blowing from east to west, and you can almost see where those Andes Mountains would be because of that dry area, and they're not even labeled on here. So using the amount of rain that we're getting, and knowing our latitudes and what direction our winds are blowing, you really can determine a lot about an area without even seeing a true image of the area. And then don't forget, our tectonic plates are going to have a role in this as well. So here you can see we've got a subduction plate boundary over here on the coast. So what we see is we see that lighter oceanic crust getting pulled underneath of that continental crust as they come together. So this is a subduction collision boundary. And that's going to force that magma up, which is actually going to be what is creating the Andes. So it's important to understand that when we talk about local regional wind patterns, weather patterns, that a lot of things are going to have a role in that, from wind patterns to solar radiation to geographic features like mountains. So lots of things go into local weather patterns in an area. So for our practice FRQ here, this is the general map. I'm going to show you a little bit more of a specific map in a second, but I want you to describe the regional precipitation pattern you would expect to see for the portion of Mexico and Central America that's indicated on the map, and to justify your answer. So here's a more focused in map for you to see. Now this is not from AP. This is just an extra map that I'm giving you. This is the actual, this is the actual AP map. Okay, so I would expect you to be able to get the same answers we're about to talk about from this map. But just to help you out a little bit, since it is kind of difficult, so some things you need to think about are the wind direction and the proximity to water. So here we're going to be having this area right here would be about 30 degrees north. Okay, your equator would be a little further south. So remember, we're going to have that air moving from south to north. Okay. Jeez. And so because we have that warm air moving from south to north, we could expect there to be more rain in the southern area and less rain in the northern area because of that warmer air in the southern region. We also need to remember those Hadley cells, so we could expect there to be less precipitation up here because of that warm air that has already risen at the equator. condensed, causing the rain to fall further south, and then the cooler air that's drier moving up to the north. So you could have talked about either north to south. So you could have said, in the south, there's going to be more rain because it's closer to the equator, and explain kind of how the Hadley cell works, which would have led you to saying that there was less rain in the northern part of the country. The other thing you could talk about here is those trade winds. So from 0 to 30, our winds are moving east to west. And so we could expect there to be more rain on the east coast of the country than on the west coast of the country, because this area is windward facing. And this area is going to be getting that air after it's already dried out and dropped all its rain on the eastern area. And one last thing I wanted to point out before we move to 4.9. So you've got two diagrams here showing you Africa on the right, South America on the left. And it's just really interesting to me that if you were to line these two countries up based on their latitudes, you can see that the 0-degree latitude in South America has very similar rainfall to Africa. And you can kind of see the same pattern happen where we go from those very heavy rainfall blue areas to less rainfall to less rainfall. And remember, that's because of those Hadley cells. All right, last section for this unit. So 4.9, El Nino and La Nina. So El Nino, this is just the southern oscillation. It's a periodic shift in atmospheric pressure, wind patterns, and ocean temperatures in the southern Pacific Ocean. Whew, sorry, guys. But it has a big impact on local weather and fishery productivity. So we're going to talk about it a little bit. So our learning objective here is to describe the environmental changes and effects that result from El Nino or La Nina events, and to show our knowledge gained, we're going to describe environmental problems in our practice FRQ. So some things we need to talk about. This is going to be kind of a heavy section, guys. I'm sorry. But it's our last one for this unit, so hopefully that gives you hope. All right, so first thing we need to talk about are gyres. So they are these large, predictable circulation patterns in the ocean, and they're due to global wind patterns. So we see the ocean kind of churning clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And that's going to be because of those wind patterns. In the northern hemisphere, we're going to see from 0 to 30 our trade winds going east. So we've got the eastern trade winds. So they're pushing the current from east to west. So it creates this clockwise motion. Okay. And so our trade winds are going to get it started over here to the west, but then as it reaches up from 30 to 60, we have those westerlies. So that's going to push that water back towards the east. So it's going to create that clockwise motion. And then we see essentially the same thing, but just flipped happening down here. So here we see our winds once again from 0 to 30 moving east to west. But then as they drop, we start to see those westerlies pushing them back. So we get a counterclockwise motion. Okay, so here we've got clockwise. And then in the south, we've got counterclockwise. So that's important to remember. These ocean surface currents are also going to create what we call upwelling zones, which are these areas in the dark blue that are shaded. So this is going to be where we're going to see the warm surface water being blown away from a landmass. And that's actually going to kind of create a suction that's going to pull up. The sun is coming in that window and I just recognized it. So it's going to pull up colder, deeper water to replace it. And we need to remember that colder water can hold more oxygen in it. So that's going to be good for fisheries. It's also going to have more sediments from the bottom, which is also going to be good for fisheries. So those upwellings produce very productive fishing areas, which is going to be an important source of money for the fishermen, for restaurants, and just in general, an important food source for those areas. So that's what I've got circled here, that water getting pushed away. It's going to bring up that cool water. And so this area right here is really where we're going to be focused at for our El Nino and La Nina oscillation patterns. Okay. So before we can really get even more into that, we need to understand a little bit more about the ocean. The ocean's super complex and complicated. So let's look at what we call thermohaline circulation patterns. So thermohaline circulation connects all of the world's oceans. It's going to help the salt content get mixed up, the nutrients get mixed up. It's going to help the temperature to get mixed up, and really just connect all these different areas to each other. Okay, so we're going to start right here at number 1. So there we're going to have some warm, very warm surface waters because they're moving up through that southern hemisphere across the equator, getting all that temperature. But then because of those westerlies, they start getting pushed over towards Europe. Okay, so that's actually going to carry warm water over towards Europe. And this is going to make Europe have a little bit more of a moderate climate compared to areas that we see at the same latitude in Canada, because that warm water is going to be releasing heat to the land. It's also going to be blowing in warmer water. But as we start to get up further and further north, that water starts to cool. So one thing we've seen along this process is we've seen some of that ocean water evaporating. Now, as it evaporates, it leaves behind the salt that's in the water because the salt can't evaporate. So as we get towards the North Pole, our water is, number 1, saltier. Number 2, it's getting colder and colder and colder as it moves up in latitude. So now we start to see the water being much more dense at the poles. So because it's more dense, it's saltier and it's colder, it's going to sink. And once it sinks, it's going to spread kind of all along the ocean floor, which is going to distribute the salt and the sediments that are in that water. It mixes the temperature up. And then we're going to eventually see it rise back up. It can't stay at the bottom of the ocean forever. So it's going to kind of just continue to get pushed down. And then eventually it will rise back up in those upwelling zones. Okay, so let's really get into ENSO now, or the El Nino Southern Oscillation. So a lot of times you'll hear these called events. We have an El Nino event or we have a La Nina event. But I want you to understand it's really a shifting pattern over time. They're all kind of connecting. So we're going to see this shifting atmospheric pressure and ocean currents in the Pacific between South America and Australia. And so what we see is a shift from El Nino, which is going to make it warmer and rainier, to La Nina, which is going to make it cooler and drier. So you can see they kind of just flop back and forth. So they are very connected to each other. And like I said, we call them events, but understand that they're not just like one-time things that happen very quickly and then are over. So what we tend to see is them peaking in a certain year or a certain time frame, but they'll have been growing before they get to that peak. And then once they reach that peak, they kind of slowly start to flip the other way. So before we can really talk too much about El Nino and La Nina, we have to talk about what it looks like normally. So in a normal year, we've got those trade winds, because remember, we're looking at that 0 to 30 area in the southern Pacific. So we're having our water blowing from east to west. So that water gets blown over towards Australia, towards Southeast Asia. And so when that warm water gets blown over, we see that upwelling happening. So South America tends to have some really good fisheries off the coast. The water is cool there, it's got a lot of oxygen, a lot of nutrients. So that's going to bring in a lot of money for the fishermen, for the restaurants, for whatever. Okay. Now, as that warm water blows across, it's going to bring heat and precipitation to Australia and Southeast Asia. So that's going to be helpful for farmers in the area. Creates those kind of moderate climates. This also, as the air rises, is going to create that low pressure system over here in the West Pacific, which is going to push our air across, creating a high pressure area in South America, which really keeps this whole pattern going. So remember that these patterns are going to be influenced by the pressure in the air, the direction the winds are blowing, the direction the ocean current is blowing. So in a normal year, our winds blow from east to west. We have high pressure in South America, low pressure in Australia, and our ocean water is also moving from east to west. Now, when we have our El Nino event, we see our trade winds start to weaken. And when they weaken, they actually reverse. So instead of going from west to east, we see them go. Instead of seeing them going from east to west, we see them going from west to east. So this is going to bring that heat and precipitation to the Americas, to North America and South America. So that's going to give us milder winters, but it's also going to give us rainier conditions, which could cause flooding. Now, this is also going to suppress that upwelling because it's going to start keeping the warmer water over near South America, which is going to damage those fisheries. So that's not going to be good for the fishermen's pockets. This is going to create cooler, drier conditions in Australia and Southeast Asia, which can actually lead to droughts if it's severe enough. So that's not good for the farmers there. And here we actually see the high pressure and the low pressure systems switch. So in an El Nino, we're going to have high pressure over Australia and Southeast Asia and low pressure in the East Pacific, so near South America. And then lastly, we've got the La Nina. So here we see stronger than normal trade winds. So instead of our winds just blowing at a normal pace from east to west, they're blowing much stronger. So you can really see that cooler than normal water reaches much further across the ocean than it did over here in this diagram. So that's going to cause an increased upwelling over here. So that's going to be extra good for fisheries. It's going to have really awesome impacts on our fisheries over here. But not so good over here because we're going to have a lot of increased rain, which can lead to flooding, monsoons. Not very good for our Western comrades over there. Okay. And in this one, we once again are going to go back to seeing our high pressure over on South America and our low pressure in Australia and Southeast Asia. So just a few reminders, little summary here. So El Nino, some bad things, some good things can happen. So you've got to kind of weigh your options. So some bad things, suppressed upwelling, less productive fisheries, less money for the local people, warmer winter in much of North America, which can be good if we're looking at it, like from my perspective, I hate the cold, so that would be good for me. But if we have a warmer winter, then we see a lot less pest die off in the winter. Things like ticks, parasites, they're not going to die off as much in the winter, so we'll see more of them the next season. Increased precipitation and flooding in the Americas, especially on the West Coast, because they're the closest to this where these events are happening. And this could cause droughts in Asia and Australia, which are going to not be good for farmers there. And not only not good for the farmers, but not good for the local people that rely on the food. And then a couple good things that can happen from this is going to be decreased hurricane activity in the Atlantic Ocean, so less chance of storm damage, and weakened monsoon activity in India and Southeast Asia, so less chance of flooding there. And then with our La Nina, we're going to see essentially kind of the opposites start to happen. So stronger upwelling, better fisheries than normal. But this can lead to worse tornado activity in the United States and hurricane activity in the Atlantic. So those are both downsides of a La Nina. This is going to lead to cooler and drier weather in the Americas. And that should say rainier, not rainier. Rainier, warmer, increased monsoons in Southeast Asia. So, to an extent, this can be not so bad for Southeast Asia if it's just a little bit rainier and a little bit warmer. But if it's severe and we start to see more and more of those monsoons happening, then those can be really detrimental to agriculture and just to life in general. So your practice FRQ, describe two problems related to the conditions of an El Nino event. So don't just identify two, describe two. What are two problems that can be caused because of an El Nino event?